So we've talked about definite integrals, and we've introduced them geometrically using areas. We've talked about some properties they observe. I spent most of the video's last section awkwardly skirting around how we go calculating areas if it turns out that we're not dealing with like a triangle or a circle or something like that. Sort of like this guy right here. So you'll notice I've set up above, I want to find the definite integral of this cubic polynomial, 2x cubed plus 1, as I let x run from 0 to 5. I have sketched a graph, totally not to scale. For the record, you can check this would have a y-coordinate of 1. This guy over here is at 251. Yeah, it's not to scale, but you should be used to that at this point. So we want to try to figure out the definite integral of this thing, or in terms of the picture, we want to measure the area trapped between this graph and the x-axis. Okay. Here's our process. So the big idea here is we're not going to try to get at it directly. We're going to approximate. This may sound a little bit familiar if you think back. That's okay. It kind of should. So what we're going to try to do is fill up this area using some kind of shape we can measure an area for really, really easily. So you could try working on different things. So I'm going to propose, let's use some rectangles as our approximating shapes, because it's really easy to measure the area of a rectangle, right? You know, length times width, or however you want to assess those dimensions. So here's our plan of attack. I'm going to take this interval of x values down here, and I'm going to cut it up into a certain number of equally spaced things. I'm going to go with 4 in this instance. So that means I can just cut this guy in half, and then cut each of those halves in half. So I get something nice and fairly equally spaced, even with my rampant inability to scale things properly. Okay, the question is, how long are each of these smaller intervals that end up appearing? So we're going to refer to that width using the symbol delta x. So that's not really a triangle, it's the Greek letter delta. If you're taking chemistry right now, you've already seen this. So the idea here is to figure out how wide each of these things are. I can take the total width and then divide that by however many little divisions I've got. So the overall length is just the difference in my interval's big endpoints, 5 and 0. Spoilers, that's 5. And then I'm cutting that into 4 equally spaced pieces. So 5/4 is a fraction. We're already approximating those, so let's just use a decimal. 1.25. Great. So now I know what my cutoff points are. I've got 1.25. I've got 2.5. Apologies for the decimals that don't like to show up. My camera is not great at grabbing those, but 1.25, 2.5, 3.75. Okay, so now we've got our breakpoints. All right, next, I'm going to shoot a rectangle up vertically over each of those little, I'll call them sub-intervals a lot, because they're kind of inside a bigger interval. Hopefully that makes sense. All right. Now the question is, how do I determine how tall each of these rectangles are going to be? I'm going to use my graph to gauge that. Technically, I could pick anywhere inside each of these intervals I like and say, well, I'm going to use my function value to determine that height. Usually we do it with some sort of consistent scheme. So what I'm going to do at first is use my right-hand endpoints to measure up how tall these things are. So over here, my right endpoint is 1.25. Shebang. And I kind of slide back over. That's my first approximating rectangle. For 2.5, same deal. These may be a little wobbly, bear with me. 3.75 goes up. And then all the way up here at 5. We got a big one right there. Yep. Okay. So now, each of these things we can work out an area for, right? Width times height, so on and so forth. Now, by design, each of these widths is the same, so we can actually kind of shorthand the process. I'll show you how momentarily. But let's go ahead and compile these heights first. So you need to leave. My board is not wanting to erase as well as it has in the past. It's gotten a lot of use in the last couple of weeks, so I guess I should be kind of understanding of it. All right, so here's what I'm going to do. I'm going to build myself a table. And that totally doesn't look familiar at all, right? So what I'm going to do is take each of these right endpoints, and I'm going to evaluate my function at each one of those. So I've taken the liberty of doing that, and I have here 4.9063, 32.25, 106.469, and then at the bottom, I've got 251. I didn't do all these calculations by hand. For what it's worth, like I said, the table may already give the game away, but yeah, you can see I just had my calculator do the heavy lifting for me. So yeah, using the table feature seems completely appropriate here. If you wanted to write this out more laboriously, you could. So now I need to add all of these guys up. Technically, you might be saying, well, wait, Professor Carroll, if you want areas, shouldn't we multiply each one of these things by their width? You're right, we should. Here's the magic, though. By design, those widths are all the same, so I can just add these up and then multiply that sum by that common width. If these widths weren't all equal, I would need to work them out individually, but it's not necessary here. So when I add these guys up, I get 394.6253. So that's the sum of all my heights. Now, I'm going to multiply this guy, that's a multiplication dot, not a decimal point, by 1.25. So normally I would just write them beside each other, but small board, you get the idea. All right, so now when I work that out, I got 493.2816. Awesome. Okay. So this is what I'm going to call a right-hand sum estimate because I used my right-hand endpoints for all of my approximations. Our textbook abbreviates this as follows. So we have an S for sum because we did a summation, an R for right hand, and then it'll put in parentheses afterwards how many rectangles you used essentially. So S sub R of 4, or the right sum, however you want to abbreviate it, that's our estimate. We can tell we've obviously grabbed some extra stuff, right? Because every one of these rectangles is poking back over and we're grabbing some extra area with all of them. It's an interesting exercise to determine under what circumstances you've got an overestimate versus like an underestimate, or if it's neither one. We don't have time for that at the moment. I'll leave that to you. Okay. You might say, well, why did you pick the right-hand sides? I mean, I just needed to say something. Technically, we could have, like I said, we could have picked any side we want. What would have looked different if we had used the left endpoints instead? Well, here my left endpoint is 0, so my rectangle kind of cuts under right here. You probably see what's happening. 1.25, slide across, 2.5 to 3.75, and I got this guy at the end. So now, using those left endpoints for this particular function, I'm underestimating every time, because if you look at each one of these, we're leaving out some area. So now in terms of how we calculate the process, it's going to look pretty similar, right? It turns out we still need the function values for several of these things again. So you got 1.25, we used him again. We used 2.5, we used 3.75. We didn't use the big guy. Instead, we use what was happening at 0. So I'm actually just going to change that 1. So it's technically more appropriate to list them in order, but again, I'm short on recording time, short on board space. My markers and erasers are wanting to misbehave because they've been overworked. Short story long, I change out the 5. I use 0 for x. Plugging 0 in here gives me a value of 1. That changes this guy by 250. So I should have 144 instead of 394. The 0.6253 doesn't change. I still need to multiply by 1.25. When I work that out, my what you'd call a left-hand sum, so instead of an R, the only thing that would really change there is an L, and I got 180.7816. Now, for this particular function, again, this doesn't work across the board, but for this particular example, we know our actual area has to live between these two, right? Because we always underestimated here, we always overestimated those guys. So we know the true area lives somewhere between our 493 and our 180. Granted, that's a pretty big window. We'll talk going forward about how we could try sharpening this up. You might also wonder, well, would we always end up using, endpoints or something like that? We don't have to. As I said, we can pick anything we like. So I want to take a look at one more example of this stuff in action. The function's actually a little bit simpler, but it's going to have an extra wrinkle tossed in. So, yep, keep watching.